Good morning. Today we continue our lectures devoted to application of constructed tools from stochastic analysis to investigation of different properties of Gaussian functions. And today we will discuss the existence of the density of solution to stochastic differential equation. Let me recall you what we have, what tools we have at this time. So we consider Wiener process. I consider one-dimensional case, and we consider the random variable alpha, which is square integrate and measured with respect to W. Then this random variables can be uniquely expanded into series of multiple Wiener integrals. We wrote these integrals in two ways. One is the following. We have the integration with respect to the cube of dimension equal to n, and an is a square integrate symmetric function, symmetric deterministic kernel. But of course, this integral must be defined, and we define it as the n factorial, and here integral over simplex delta n, the same, where delta n is set where coordinates T1, Tn are ordered in decreasing order from 0 to 1. After we have such Wiener expansion, we defined stochastic derivative of the random variable alpha. It is a random function now. D alpha t is equal to sum from n equal 0 to infinity. Here n, and here is 0, 1, n minus 1, an t, t1, tn minus 1, dw, tn, dw, tn minus 1. So we, when we want to calculate stochastic derivative, we just shrink the multiplicity to n minus 1, put here multiplier, and take one value as an argument of the stochastic derivative. In this repeating this, we can get second stochastic derivative, third, and so on. We proved that D is unbounded but closed and densely defined operator on the space A2 sigma W with the values in the space of square integrate random function. We defined conjugated operator E, which we call square-root of extended stochastic integral, and its name is confirmed by the following property. If xt is a random function such that x is adapted to the flow of sigma field generated by W, then one can define stochastic integral, and it occurs that the Skorokhod or extended stochastic integral from x also exists and is equal to integral from 0 to 1 xt dwt in intersects. This is Ito integral. But we were able to show that not only adapted random functions belong to the domain of extended stochastic integral. Namely, we proved that if the random function has a stochastic derivative, then if x has dx, then x belongs to the domain of definition of extended stochastic integral, and moreover, expectation of ex squared can be calculated by the following formula. This expectation of the norm of x squared plus trace of dx squared. Here I just recall that x is a random square integrated function. So here is the norm in H201, and its derivative now is random Hilbert-Schmidt operator, so its square is nuclear operator with well-defined trace, and one can consider the following mathematical expectation. Moreover, it occurs that this trace is not always non-negative, because here is simply dx and square, and dx is not self-adjoint operator. So it can happen that we get here 0. Such example we considered last time. So this Skorokhod integral has interesting properties. One of these properties is the following. When we consider Skorokhod integral from alpha x, so we multiply our random function with the random variable. We suppose that this random variable has stochastic derivative and is bounded together with its derivative. Then it again is well defined and is equal to alpha multiply x minus the integral from 0 to 1 x e d alpha t. So these are the properties of extended stochastic integral, which we already have. And now it's time to discuss stochastic properties of solution to stochastic differential equations. I will consider the following Ito stochastic differential equation. dxt is equal h xt dt plus bxt dwt. X for 0, I will suppose is equal x0, which is non-random deterministic number of the real line. I suppose that coefficients a and b are smooth enough and bounded. It means that they have two continuous, the last one is continuous, derivatives, and they are bounded together with its derivatives on the real line. So now let us check whether xt can have a density. So the question which we will discuss this is the following: existence of the density of xt. Let us proceed as follows. Let us try to connect existence of the density of this random variable with the properties of its stochastic derivative. To do this, let us begin with the general situation when I will substitute this solution to Cauchy problem xt by some arbitrary random variable. So let's start from the following simple lemma. Lemma. Let random variable alpha be such that there exists c greater than 0 that rho phi which belong c1 0 so it is continuously differentiable functions with the compact support. We have the following: the expectation of phi prime from okay, maybe I will omit this and just put here bounded. Please correct this. Phi prime from alpha is less than c, and here we have norm of e uniform. I just take expectation of derivative of such function and introduce that for the universal constant is less than. Then there exists density E for distribution of. Let us check this. Because it's not too hard. Now I will consider the following function. I will take the interval AB consider the function Pn such that it's better to draw a graph. Here is interval a, b, and here is 1. So this will be the following function. Maybe function phi n will approximate this one. So phi n will approximate this one smoothly. Phi n converge to the function p, which is equal to 0 when when u is less than 8. Here is u minus a divided by b minus a. No, and multiply b when b, it will be equal b. When u is from a b, and then it is equal to b, and it is equal to b when u is greater than b. So we consider the sequence of smooth functions, which I use as I draw here and here, which converge to the function phi. Then, consider this sequence. One can apply Lebesgue theorem and say that phi n prime will go to indicator of RAB and pointwise, and phi n go to our function phi. Then one can check that since we have inequality, for any n which is greater than expectation of phi n prime or alpha less or equal than c of the uniform norm of phi n. And then the same remains in the limit. The same remains in the limit because phi n uniformly tends to phi. And here we have pointwise convergence, so we can apply the Lebesgue theorem about the dominated convergence. So we will have the expectation of indicator from interval AB alpha is less or equal than C, and here is B minus A. This is the uniform norm of our function phi. The last one can be rewritten as follows. That probability that our alpha belongs to the indicator to the interval AB is less or equal than C B minus A. Actually, this means that our distribution is absolutely continuous with respect to the back measure due to this fact, and even more, it means that the obtained density of B alpha minus 1 is absolutely continuous. with respect to Lebesgue measure. And moreover, density is not greater than this constant C. And density P alpha U is less or equal to C. We finish our proof. So now we understand what we need. Maybe we need to estimate the expectation of the following part.
I have a question.
Please.
But the lemma does also hold when we only want the inequality to hold for smooth functions, for infinitely differentiable, then the lemma would still hold, according to your proof.
Yes, surely. Of course, it is understandable that we can have just modernization of this lemma to adapt it to our proposals. I showed only one variant in order to get the idea why we estimating such expressions uniformly with respect to some family of functions. You are absolutely right. With respect to some family of functions, if we have such estimation, then we have a density. So we need such estimation for sufficiently large family of functions. Of course, it can be shrinked from those which I proposed. Thank you.
Okay, thank you.
So now we understand what we need. So let's come back to our stochastic differential equation. We have to estimate the following function, the following mathematical expectation, x t. If we will be able to get something like this, then we can make a conclusion about existence of the density. So our idea is to use here stochastic derivatives of this solution. So let me show how we can try to do this, and after this we will see the existence of the stochastic derivatives and its properties in order to make our considerations much more rigorous. So let us try to proceed as follows. Suppose that there exists stochastic derivative of xt. Then I can rewrite this formula as follows. It is equal to expectation of phi prime xt, and here I will do the following. Here will be the norm of dxt squared, and I will dxt. Suppose that I can do everything, so it is not zero and so on. Let me recall you that dxt now is a random function, so this norm is the norm in L201. Then I can continue. I can continue. And put here expectation prime xt here is the non-infinite space can be considered as a scalar product of the vector onto itself. So we have this one dxt and here is one of the more dxt square. Then the next one, I will put this is a random variable, and I put it inside of the scalar product. So finally, we will get the following expression. Is equal to expectation of what? Here, the scalar product p prime xt dxt, and here is dxt over mod dxt. Now it's time to recall that the stochastic derivative has a lot of good properties. So it's satisfying chain rule, and this expression can be rewritten as the expectation of the stochastic derivative of phi of x t multiply on the dxt norm dxt square, and finally we get the expression which looks like the expression from the definition of extended stochastic integral. Let me erase this intermediate formulas, and I will recall that extended stochastic integral and stochastic derivative are connected as follows. If we have the expectation of the scalar product of d alpha multiplied with some random functions y, then it is equal to expectation of alpha multiplied on the extended stochastic integral of y, of course, if everything is well defined. So now suppose that we have the situation when this random function, which plays rule of this y, is in the domain of extended stochastic integral. Then I can continue, and I can finally get the following. This is expectation phi of xt multiplied by the e of dxt over norm of dxt square. Okay. So the further steps are very common, trivial, because we can continue recalling that phi is bounded. So if we take the absolute value of this one, then it is less or equal than norm of phi infinity multiplied by the expectation of the absolute value of this e of dxt over dxt square, and it is less or equal by Cauchy inequality than a norm of phi. And here we have the square root of the expectation of the extended stochastic integral dxt divided by log of dxt square is square. That's all. So we see that if we will be able to check that solution to our stochastic differential equation has stochastic derivative, and moreover, that this ratio is in the domain of extended stochastic integral, and will be able to estimate all these things, then we have the conclusion that our solution xt has a density which is bounded. What is good here, that today we already recall that there is a good sufficient condition for random function to be in the domain of Skorokhod stochastic integral. It is existence of its stochastic derivative. It means that this expression must have stochastic derivative. So roughly speaking, it looks like that if x will have a second stochastic derivative and its first stochastic derivative has a norm which is integrated in negative power, insufficient negative power, then we have it. And it is true. So let's go to the checking of these properties for solution to our Cauchy problem. If we will be able to check that this is well defined, then everything is okay. And we have conclusion that our solution has density. Let me recall you the equation. Before to start, let me recall you that dxt from s is equal to 0 when s is greater than t. Maybe you remember when we discussed this, that if we have the random variable which is measured from the sigma field ft generated by the Wiener process, then its Ito-Wiener expansion has the kernel which are equal to 0 after t. So xt has Ito-Wiener expansion like sum from n from 0 to infinity. Here is multiple integral from 0 to t, not to 1. Due to this, we understand that if s is greater than t, then this stochastic derivative is equal to 0. Now let's try to get the equation for stochastic derivative of our solution. In order to do this, I will rewrite our Cauchy problem in the integral form. So then we will have that xt is equal to x0 plus integral from 0 to t a xs plus integral from 0 to t And then let us differentiate. Let us formally take stochastic derivative for both sides. Suppose that it exists, we will get the equation. Then dxt at the point S is equal to, let us recall, S is less than T. It is essential. It is constant, so its stochastic derivative is equal to 0. Now, what we have here? Here we will have the integral from S to T, not from 0. Why? Because when this argument, for example, we have xr, when r is less than x, then we discuss it. The stochastic derivative of xr is equal to 0 at the point S is equal to 0. So due to this, we have here integral only from S to T. Remember chain rule, A prime xs dxs at the point R. The first argument, first time argument, as here, is related to the time argument of the initial function x, and the second one is argument of stochastic derivative. Second one is excuse me, exactly in opposite direction. R, and here is R, and here is S. Second one is argument of stochastic derivative. dr plus. Here it is stochastic integral, and we already differentiate with stochastic integral. And we know that there arise additional term in this in the stochastic derivative of stochastic integral. And this additional term looks like b x s plus, here is integral from s to t b prime xr dxr s dw r. That's all. So we have the following equation for stochastic derivative, and it can be seen that this equation is a linear equation with respect to unknown function. This one, and this one, and we start from bxs when t is equal to s. From this point of view, it looks like we have a good solution to this equation, and moreover, this solution is the stochastic exponent. We discussed it with you, the form of the solution of a linear stochastic differential equation, and it looks like exponent. If we have no these terms, this is usual exponent. We have the exponent of the integral of this one in the power. But if we have ito term, the stochastic exponent has slightly modified kind, but still it is well defined and has very good properties. Let's write the solution. So we have the following solution to this equation: dxts will be equal to bxs multiplied by the exponent of integral from s to t a prime xr dr plus integral from S to T B prime XR dr WR, and we mentioned e to term minus 1/2 of the minus 1/2 of the integral from S to T B prime XR square dr. That's all. So we have the following solution to obtain the equation. Of course, we need some technical work in order to prove that this solution is exactly stochastic derivative to our of our initial solution xt, but it can be done using the property that D is closed operator. And after this, let's look what we have here. We have here the exponent of the following kind. Let me recall you that B prime and A prime, we suppose, are bound. Then I can say that here we have a martingale with a bounded characteristic. Yeah? From this point of view, I can say that the one of the norm of dxt is integrated in any power, in any, let me say, for example, n, but expectation is less than infinity when for any n which is greater than 1. So this is A2 norm. A2, 0, 1. This is a good news. The estimation is rather standard and is following. This and this estimate by constant. Here, what we have here martingale with bounded characteristics. So its maxima on the interval 0t can be estimated as a maxima of the Wiener process on some interval which is defined by the constant which bounds B prime. So we have this this relationship. Also from this this relation, one can check that X has a second stochastic vector, but it can be obtained from the equation for the first, that X really has a second stochastic derivative, which also can be expanded, can be expressed as some integrals with the stochastic exponent. I will not write the expression for the second stochastic derivative of X because it is not too nice as this one, but I just note that there is D prime, second stochastic derivative of X. Then unite together obtained knowledge. One can say that the integral, integral from integral there exists from dxt divided on the amount square, and consequently there exists a density. Then it follows that xt has a density. Of course, this is just the preliminary result. because one can consider not only five such expectations, phi prime of xt, but one can consider functions of special kind like exponents here, and then get more serious estimation for density of xt, not only that it is bounded by constant, but it decreases like Gaussian density on infinity. Also, suppose that we can continue this procedure for a moment. Suppose that we can put here second or third derivative and get the same estimation. Then it looks like our density becomes to be differential function. And it is true. We can do this exactly in the same manner, but with a more complicated calculations. But only complicated calculations, the idea is already done. This means that due to our stochastic calculus, we will be able to prove that xt has a good density, not only density, but infinity, even infinity differential, smooth density. Now let me recall you what does it mean for partial differential equation. Let us connect to our stochastic differential equation. Let us connect the following partial differential equation. This is a parabolic problem, namely d of u capital, which depend from x small and t, is equal to 1/2 of b square x d2 dx square ux t plus plus ax d over dx ux t, and I suppose that we are solving this partial differential equation in the domain x belongs to R. T is greater or equal to 0, and with the initial condition ux t is equal f from x, excuse me, not t but 0, is equal f of x, where f is some bounded continuous function. F belongs to CB. As usual, we define the solution to such parabolic problem as a function which is twice continuously differentiable inside of the domain, continuous up to the boundary, and coincide with this value at the boundary. And let me recall you what we call fundamental solution to this equation. Yeah, let me. Unfortunately, I have to write something. Maybe this one. So, suppose that we are looking for the fundamental solution E x y t. It will be the following function, that if I integrate f of y dy, then I will get solution ux t for arbitrary bounded continuous function f. Yeah, So the existence and good properties, fundamental solution to partial differential equation is an interesting and important problem, because if we have fundamental solution, we get the solution for any initial condition, and if we have good properties, for example, smoothness, good differentiability of fundamental solution, then we get the good properties of this solution to partial differential equation. So the question when it exists is important. And as I said, Lars Hermander was a person who solved the question completely for parabolic equation in multidimensional case, and he produced the condition which is now named due to him, so-called Hermander hyperpolarizity condition. And in our case, it looks like the coefficient must be non-zero. Actually, now let us see that we also solve this problem. Why? Because let me recall you that for this solution, due to the Feynman-Katz formula, we have a good probabilistic representation, namely uxt. I write this one. uxt is equal to expectation of f of x t, and I will put here small x, which means, as usual in the theory of Markov process, that x of 0 is equal to x small. Excuse me, just a second. Алло? Да, все нормально, да. Все отлично, я думаю, где-нибудь без 15-12. Да. Да, до встречи. Okay, sorry. So we have such a representation. Now suppose that this random variable has a density. We proved it already. So I can continue. And I can write it as an integral with respect to r. And here is f of y. And here is p x, because we started from x small. T, because we looking at the solution in the moment time of t, and y because of here is integration. Let's compare these two formulas. And this density occurs to be exactly the fundamental solution to our partial differential equation. So now we can say that if our equation has bounded coefficients a and b, that they have two continuous derivatives, and b is non-zero, is separated from zero, then we have the good fundamental solution to parabolic problem. This is a way how Malad and Bismuth overcame difficulties which exist in analysis in via deterministic approach to the problem of existence of the fundamental solution to parabolic equation, at least to parabolic equation. It occurs that Malevin calculus, this is the part of stochastic analysis which apply our tools which we discovered during the semester to the problem of existence of the density, can be applied not only for parabolic problem, it can be also applied for Dirichlet problem, for example. And moreover, Evgeny Borisovich Dynkin was a person who created the same approach, but to non-linear parabolic equation, non-linear with respect to function u. He invented so-called super processes, super diffusions, and it's the same. So such approach nowadays became to be very common. And when you will need to check the existence of the density of some random variable in statistics, in order to get some good statistical test. In partial differential equation, in order to get some properties of fundamental solution, you can use this approach, and it works. Moreover, people discovered now introduce stochastic derivative with respect not only linear process, but with respect to much more wide family of processes. So anybody who wants to have density create his own stochastic derivative and proceed exactly as follows. This is the end of our lectures in this semester. Thank you for attention. We will have an exam in June 12th. I will send the questions the next week. Thank you for attention. That's all. Maybe somebody have questions or comments. Okay, if not,
Sorry, can you repeat when the exam is? I didn't hear it.
Exam will be June 12th.
Okay, thanks.
Okay, bye.
Bye.